Okay, so the talk I will present today is about one-shot optimization. So in this talk, we will present you some kind of counterintuitive result that occur in one-shot optimization. This is a joint work with Olivier Teto, with my advisor at Facebook, and also colleagues at Dauphine and also University Pierre et Marie Curie in Paris. So um, I can move. I can't. Oh yes. So let's first remind a few things about what is a one-shot optimization. It's a pretty simple setting. We try to find the best sampling strategy to optimize function f. So we have to choose a lambda point, and how can we infer observing fx1 and until fx lambda? How can we have a good approximation of the arc minimum of f of x? All xi are evaluated in parallel, which means that we are in a random search or a quasi-random if we take quasi-random sampling instead of pure random sampling. And this is a usual setting in hyperparameter search, for instance, in machine learning, where we can sweep all the hyperparameters to optimize and find the best model. In the following of the talk, we will focus on the sphere function centered in some parameter x star. The parameter x star will have some assumption in the two results we will show, but we will see later what are the assumptions made on x star. The results can be generalized to other function, but to more wider class of function, but in this talk, we only focus on this class of function, and but I've worked on losing this assumption of sphere function, and we can do something which is pretty much which is more loose. So that's cool. So we will denote x parenthesis 1 until x parenthesis lambda the ordered values, which mean that f of x parenthesis 1 is less or equal than dots, which is less or equal than f of x lambda, parenthesis lambda, where lambda denotes the John sample of the problem, and we will denote also d, the dimension of the problem, which will be an important factor in our result. So the strategies we will study are the following. We will try to we will have a prior on x star, which is we don't know exactly where is located x star, but we have some assumption on that. For instance, we can assume that it's drawn from some distribution. We also suppose that xa are IID sampled from some distribution that we will define, and this distribution might be possibly different to the prior distribution. And the second strategy we will study is given the mu best indices, what is the error made using the estimation that consists in averaging the mu best points? We will see that it breaks some kind of the curse of dimensionality in this case. So first, let's assume that we have this function f of x, which is the norm of x minus x star, and we suppose that x star is drawn as a standard Gaussian distribution, and we focus on the two following issues, which is first the scaling strategies. How do we choose the sampling of of sigma of the variance of the sampling given lambda and d, and how do we choose mu given lambda and d in the scaling, in the averaging strategy, which are the two strategies we aim to study today. So first, we focus on the rescaling strategy. So let's assume that X star is distributed as a centered Gaussian distribution, and consider the following objective function, which is basically the quadratic function, the sphere function with with a random point optimum. For this strategy, we define the regret as mean on A of xa minus x star, and it was shown in Kowat et al. That if lambda is not exponentially dependent of the dimension, sampling only 0, which means like norm of x star will be lower than the minimum of the norm of xa minus x star. Yes, so it will be, so it's some kind of counterintuitive result that it's better sampling only 0 than sampling lambda points from centered Gaussian distribution. The question one might ask is, how do we choose the scaling of the distribution we sample from the point in order to minimize the regret? So the strategy is the following. We suppose that lambda depends on d, because otherwise we can't make anything. We suppose that lambda goes to infinity and d goes to infinity. And we suppose that log of lambda is in small o of d, which means like log of lambda is very small divided by d is very small. So we interest in finding conditions to find epsilon and sigma, to find epsilon and sigma, such that the probability that our regret is better than only sampling 0. We show in our paper that first, if there exists C1 and C2, such that the regret is of the gain factor is of order log lambda divided by d, if the scaling is of order log lambda divided by d. We show that we also show that if we want sigma positive and epsilon positive, then we need to have sigma less or equal than log of lambda divided by d, sigma squared, my bad. And we also show that in order, we can do better than gaining a factor of log lambda divided by d. So this factor log lambda divided by d seems to be optimal to sample to have the lower regret as possible, and that's what we also observed experimentally. Here we observe the rescaled variance, which is the variance divided by square root of lambda divided by d, and the average regret. And here we see that we have some kind of an optimal value for sigma star, which is of order square root of lambda divided by d. Here we also show that this results holds for a more complex class of function. Meta-chain recentering is the method we proposed, we just proposed, and we show that this method is far better from other methods that that are usual in one-shot optimization. So now we are going to focus on the averaging strategy. So the averaging strategy consists in the following: you have some point x star, and you sample your point, and you average the mu best point, and you interest in the regret of this strategy, which is the norm of the average minus x star to the square, to the power 2. The standard and usual strategy that we present before consists in using mu equal 1. Here, this strategy is a bit restrictive, and we will show that it's even suboptimal in some sense. The strategy, the setting we will suppose is that we sample the point x1 x lambda in a 2D, in a d-dimensional L-tubal of radius r, and we will suppose also that the optimum x star is inside the ball. And we will denote epsilon, the ratio between the norm of x star and the radius of the ball in which we sample. In our second paper, we show that for mu equals 1, we suffer from the curse of dimensionality, which is that the regret of this strategy is of order lambda minus 2 divided by d. This is a minimax rate. And also we show that for a good choice of C, which is a C less or equal than 1 minus epsilon to the d, the regret with mu equals to the floor of C lambda is of order lambda minus 1 as lambda goes to infinity. So here it seems like we broke the curse of dimensionality in this case. But there's always a but. To do so, we need to sample a lot of points, because if D is big, here 1 minus epsilon to the D is very, very small, and C is as a consequence very, very, very small. So we have to sample a lot of points, but asymptotically the regret is better sampling using this sampling strategy instead of using only mu equals 1. So we explain this also explain why when we are close to the optimum in evolution strategies, for instance, like CMIS or other variants, choosing the average of the best points lead to a better strategy than only keeping the best point. So the key of the proof of this result is the following: is we need to condition the expectation of this thing to the value of x parenthesis mu plus 1, because the average here will be independent from to the permutation because everything everything that is inside the level set of f of x mu plus 1, it's like if we resample, we don't care. So here we can take the average conditionally to the average of the mu base point, but without taking into account the order if we condition to the value of x mu plus 1. And here we compute then for mu equals 1, for mu 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 unknown, for mu whatever you want, and then we link the two, and then we use condition bias rule to prove the result. So this result is quite of counterintuitive, but if you really think about it, it's some kind of trade-off bias variance, the trade-off between bias and variance, which is like when mu, when you are close to the optimum, if you sample your point, you have to sample many points, and here the average will be a debiased, low variance estimator. But if you're far from the optimum, maybe keeping only one point will be a better strategy, because you will have a lower regret, and you will have a lower bias, but a higher variance. But here, when you're far from the optimum, the bias will take the lead. So to conclude, we have shown two counterintuitive results. Sampling with the same variance as the prior distribution is suboptimal, and also returning the best sample in one-shot optimization is suboptimal. So that's why we call the talk revisiting one-shot optimization. But as further work, we want to prove results beyond the sphere function, which I've done but not submitted or published yet. After, we want to prove result for the Gaussian sampling in averaging strategy. It's a bit more technical, but we've not worked on that yet. Combine both strategies, because I think we can have good experimental result combining both strategies, and also derive an iterative algorithm for the averaging strategy, and maybe find some kind of iterative population size, adaptive population size in evolutionary strategies, for instance. So thank you for your attention. And here is a bibliography I mentioned in the paper, in the talk. So thank you.
So thank you very much, Laurent, for a nice talk. Again, any questions? I will ask one, just to give you time to ask one.
Yeah.
There's one thing maybe I didn't get complete. So you want to generalize this to other functions also, right? If possible.
Yeah.
Do you also think it's possible to say something about functions that don't have a unique minimum? Right? Or is it just the flavor of the problem that you have some distance function to some point or something?
Actually, I can talk of what I've done so far. I suppose I've worked on function that will be smooth and strongly convex close to their optimum, and I suppose their optimum is unique. Because if they are multimodal function, I think it will be more complicated to prove such result. And even the result for averaging will be wrong unless this set of optimum is convex, I think.
Sure, that would be my second question, because if you don't have one unique minimum, then averaging actually destroys a possible good result, right?
Yes.
So, okay. Thank you. So, any other questions?
I have maybe one question. I remember there was a paper of Olivier Taiteau and other people. They looked here at one-shot optimization, and they used quasi Monte Carlo points. So don't did random sampling, but used quasi Monte Carlo points. and that lead to better results. Is there maybe some hope to, let's say, combine quasi-Monte Carlo points and your averaging technique to obtain better results than just doing random sampling?
Actually, when we evaluating our strategies, we used both random strategies and quasi-random strategies. So, and we show that we got better results using quasi-random sampling than purely random sampling.
Okay, thank you.
Okay, I think this was quite some time to ask questions due to that in the chat. So it seems there are no other questions. So thank Laurent again.
Thank you.